third of our series of mathematics and AI. And we are delighted to have today Gunnar Carlsson from Stanford University and Blue Light AI Inc. The title of his talk, Topology, Data Science, and Deep Learning. Thank you very much, Gunnar, for coming.
Thank you. Thanks for the invitation. I've spent my life doing both pure and applied work in the form of data science originally, but now with artificial intelligence, it feels to me like there's a real synthesis that's coming around. I actually don't feel like the two are that different, to tell you the truth, but if you start thinking about them in the right way. And so, in particular, though, of course, AI, as it relates to math, can be divided into two parts. One is AI for math, where you try to get the machine to prove theorems, and the other is math for AI, where you try to use math as a powerful set of techniques to improve and understand, the complicated, neural networks. I think everyone would agree that we don't have a full understanding of how they work, and that we certainly don't know how to control them completely. So what I want to talk about today are things in the math for AI direction. Okay, so I want to show you some small contributions that I think point in interesting directions that one can do, and I'll show you some examples of how they've worked out. Okay, I'm having trouble getting the sheet.
You should send it to
Sorry, there we go. Okay. Okay. Anyway, AI is clearly one of the great intellectual advances of our time. Everybody knows it. It's a piece of technology that's actually out there in magazines, on the web, and the newspapers. Let's talk about old times. It's achieving fantastic things, but there are definitely some issues. So first, it's viewed as a black box, which is really a problem in many ways. It means that we can't control it predictably, which is certainly what we would like to do with any kind of technology. And this is a particular problem in a lot of very heavily regulated industries, like healthcare, like financial services, and even insurance. So that's a general problem about us not understanding it, but a more particular problem is in what's talked about as post-training. So, many companies, they don't want to use a machine that does everything and just try to plug their stuff into it. They know that won't necessarily work. So you need to do post-training in various ways. And what that means is somehow you train. Either you train the model again on your specialized data, or somehow you feed things into it. You somehow incorporate information about your specific area so that you can get it to do what you want with precision. Because one of the things that I think we've probably all found, and I found it just by trying to ask it about math. I found that when you take, the Gemini, say, and try to and ask it some high-level math questions, it does really well at the high-level stuff, because it'll tell you, oh, this relates to that, and oh, there's a connection here. But at a certain point, when you start to get too precise in your questioning, somehow all of a sudden it doesn't acknowledge that it doesn't know the answer, but it just gives you a BS answer. Pardon my French. So I think that's a very interesting thing. So what I want to talk about today is sort of under the heading of maybe of generalized signal processing. That is to say, when we think of signal processing, we think of radar and sonar and audio and video. And those involve serious mathematics, serious traditional mathematical methods for the modeling of data and for making the algorithms work. So there, it's absolutely critical to provide the features in the right form, exactly the right form, in order to understand the data and to build good modeling for applications. So that's like radar and so on. Can one begin, the question I want to ask is, can one begin to get systematic about analogs to signal processing, but instead for, for artificial neural networks of some kind or other? Okay. So I'm going to discuss some examples where we've carried out, the beginnings of that. So just to give diagrammatically here, what I mean here is you can view schematically the process of doing data and AI. Data goes into the algorithms, and then there's output. By the way, for AI, there's stuff to be done at all parts of this, like, the ML AI algorithms you can modify architectures, and that can be very useful to modify those things. You can even take the output and attempt to build decoders for the output. But you can also work with the data and have, the raw data come in and having it processed by some signal processing kind of algorithm to produce good features that actually will improve things, or at least that you can test what happens when you feed those features. And so what I want to focus on today is this part right here. Not to say that there isn't a lot to be done in all the others. There's plenty to do in all. Okay, so I'm going to talk about three things. I'm going to talk about convolutional neural networks, which are basically the AI that is used for images. I'm going to talk a bit about large language models, and then also feature creation using autoencoders. So let's talk about convolutional neural networks. So first of all, maybe I'm telling you something you already know, but nevertheless, this is a part of math thing. So let me just go through this quickly. Neural network architectures for modeling and analyzing image data sets. Those are convolutional neural networks. They consist of neurons, and they're organized in layers. So the neurons are kind of the features. Each of them has an activation or a firing. And then you have the layers of lots of these neurons, and each neuron in one layer is connected to some neurons in the preceding layer, and it computes its value, its activation, as part from those features that it's connected to. So the architecture is specified by a directed graph structure, and with neurons as vertices and edges that specify the formula for computation. So the activation function is a fixed real function which is applied to a linear or possibly an affine linear combination of the connected neurons. And those coefficients and possibly that constant term, the bias, as it's called, are called weights. And those are the things that are learned. So as the whole learning process is an optimization process. That says you need it optimized so that you fit the data and the output that you want. And it's done over this very large space of weights within the neural network. So in large language models, those number of weights are in the billions and trillions. So first of all, the simplest version is just this. This is the one I mentioned there. You see the different layers, and you see the arrows connecting there. And so if I look at that lowest one in hidden layer 1, that neuron there is connected to, in fact, all three in the red layer there in the input layer. Okay. And so here's, I mentioned it in words, here's the activation function. So here you can look at that and you can see that this activation here, it's getting some weights coming in with W0, W1, W2, which are being multiplied times the activations in the preceding layer, X0, X1, and X2. You sum those together and apply some nonlinearity, some function f in there to produce an output. There has to be a nonlinearity there because if there wasn't, you would simply be doing ultimately a linear regression problem. So, okay. Now the convolutional, what I just told you about there was called a multi-layered perceptron. It's got multiple layers like that. The special thing about convolutional neural networks is two things. It restricts the connections that can be made, And also it has a degree of symmetry to it. So here's the thing. In the case of a convolutional neural network, the layers consist of collections of grids of neurons. So if your image is, say, 100 by 100, then each layer will consist of a lot of 100 by 100 grids. So that it's retaining the geometry of the set of features. The requirement of the connections is that, well, if I have a particular pixel, it can only affect the values of pixels that are nearby in the next layer. So there's a locality there. So if I've got something in the upper left-hand corner, a neuron, it will not connect to something which is in the lower right-hand corner. Okay. But and also, so that's one thing that says, well, we need to take into account the fact that we're dealing with data that comes of a particular form. In other words, it's supposed to be, it's an image. And so you wouldn't want to just view it as a bunch of numbers with no organization on that pixel set, because you would lose so much information. And so instead, you keep track of it and you build it into your network structure. It's also translation invariant. So in the sense that if I have some stuff in the upper left-hand corner that's indicating that you have a cat up there, that same pattern has to exist in the lower right-hand corner for detecting cats. So in each one of these grids that occurs in a middle layer, you have this translation invariance. So those are the two things that make the convolutional neural network special, and that's what's responsible for the power. Because when you did things before, when people tried things before, without that kind of preliminary organization, it just wasn't very successful in studying images. So here's a picture of it. You can see here, I've got each layer organized into grids, and you can see there that I'm connected, but in sort of a local fashion. It doesn't indicate the translation, but just think of sliding those black rows up and down and right and left, and they move correspondingly in the next layer. Okay. So anyway, there's this equivariance and there's locality of the connections. Okay, so here, if we suppose then that the locality is such that actually you connect only to your very nearest neighbor. So it connects, you've got a pixel and it's going to connect to a 3x3 array around it. So there's options where you can make it larger and so forth. But let's just think about that. So one goal would be to then analyze the most frequently occurring weight patterns. So like each of those patterns then is a 3x3 array of numbers, which is coming in. And so you want to understand, what does the machine compute frequently? What patterns what kind of patterns does it compute? That should give us some beginnings of an idea about how the CNN is performing its tasks. So how are they organized? What should we expect? And so I want to look for answers in natural image statistics. So I'll go through now. This is this is an old piece of work, but nevertheless, I think it might be helpful here. Mumford data set was a data set constructed by David Mumford and a group around him at Brown. They took a lot of, like 5,000 natural images and collected 3x3 patches from them. And they filtered them by variance. So in other words, you don't want to include constant ones because they'll dominate the statistics. But if you choose them something with at least a minimum amount of variance, then they built that data set. Do we expect that to have any kind of structure to it? Well, maybe. Let's see what happens. So they constructed, as I say, a set of about 8 million of these. What can be said? So there's a notion of homology in algebraic topology, which performs and gives you counts of the number of holes of various dimensions. So it finds connected components, that's at H0, and the count is called a Betty naught. There's loops, you count redundant loops, and there's also, it produces a count of those. And similarly for in dimension 2 and 3 and 4. So, on the data side, you can't do that. You don't have continuous objects. All you have is kind of samples. And so what you need to do is you need to build something that accomplishes the same effect. It's called persistent homology. Its output, rather than being numbers, is instead these things called persistence diagrams or persistence barcodes. So if you look there, you can see the circle at the top has a long bar in it. This is a so-called Betty-1. So this is the barcode for counting loops. And there's a loop there for that statistical circle. And when you have two statistical circles, you can see you get two of them. The bottom one there is a data set that is disconnected into a lot of components. And what you get then, when you compute Betty naught, so that bottom one is actually a Betty naught, which will give you a count on the components. But it's a multi-scale thing, right? So in fact, it keeps track of loops or connected components at various scales. So here's what happens when you apply this to the Mumford data set. And what I will say is, you see there's a k equals 300 up there. That's a choice parameter in the density estimator, because we want to compute only the densest things that occur. If we choose everything and try to compute it in any statistical situation, you will get nonsense, because there's always little outliers. And if you don't, filter out, very low density things, you never get any reasonable answers. But so that parameter there is something about the density estimator. I'm going to vary it here in a minute, but for now, let's leave it fixed. And we take the 25% densest points in this Mumford data set, and that's what comes out. So you can see that looks exactly like the bar that I had before when I was defining Betty numbers for you in the last slide. So this suggests that this is a circle. And the question is, what's the explanation for that? Well, the explanation turns out to be very simple. It just says that linear approximation of patches is a good thing. That is to say, you get a circle there. This is something which is studying, linear gradients at various angles. Okay, so these are edge detectors at various angles. So, if you say, well, gee, I could have thought of that. But now suppose I change my density estimator a little bit. I'm going to make it a little bit more refined. That is to say, I'm going to count points closer to where I am rather than farther away. And then this comes out. And what comes out, it's always 5. It's not just like, oh, there's random stuff going on. So it's always 5. And what's the explanation for this? Well, it's something called, ended up calling the 3-circle model, which is, 3 different loops. One, that black one, is that first loop that we saw in the previous situation. We call it a primary circle, but then there's 2 secondary circles. And you can see that this thing is Betty-1 equals 5, first of all, right? The picture that I drew, we're topologists, so we're able to move things around and say this gives us Betty-1 equals 5. And so a secondary circle looks like this. So this is actually sort of transitioning from sort of 2 primary circle points, which are at the north and south poles. And I'm sort of passing through something that looks more quadratic, but in that same direction. And so the 3-circle model looks like this. So what you can see there is that these, this right here is the same as that. This is the same as that. So they're actually glued together in that way. Okay. So the question is, this is all one-dimensional. Is there something two-dimensional that this fits in, something that's maybe more symmetrical and so on? And the answer is, yeah. When you do it, you get this coming out. So this now describes Betty naught at the top, only 1, so it's connected. Betty 1 is got 2 long bars in it, so that's a Betty, Betty 1, 2 holes. And then the top one there's a Betty 2, which is a 2-dimensional hole, and that's also a 1-dimensional. So you could say, oh, well, if you had done the first couple of weeks of an algebraic topology course, you'd say, oh my goodness, this must be a torus. Okay. But in fact, it turns out there's a classification of 2 manifolds. Yes, there's a torus, but there's another one which has the same, and these Betty numbers are mod 2 So in fact, there's one called the Klein model, which has these same mod 2 Betty numbers.
Why are they mod 2?
Excuse me?
Why are they mod 2?
Oh, for computational reasons. We actually went ahead and computed mod P also, and then you get a different answer, which tells you that it had to be the Klein bottle, because when you compute this mod P, this one, mod 3 say, this one goes away, and there's only one there, so.
Is that the state of the art with TDA pipelines that they do ZMod 2, or is it?
No, I won't swear to it, but I'm sure there's something that will do certainly, calculations for, a lot of odd primes and so on as well.
Or like integer or rational, or?
Even that, yes, there are, it all depends on how reliable you want the software to be and so on. I think the integer one is probably still somehow in development. The problem being that there isn't actually a precise classification in the way that there is over a field. But over rational numbers, yes. Okay, and so anyway, so how does this Klein bottle work? How does it organize things? Well, you can see here, what is the Klein bottle? The Klein bottle is something that's gotten by making identifications like these. So you can see I identify the bottom with the top without a twist, but the side with the other side with a twist. So that's the Klein bottle, and it fits very nicely with our discussion here of the primary circle, which sits there. Notice that's a circle because the upper right is connected to the lower left and vice versa. The two secondary circles sit like this, so they are connected to each other, and then they all fill out the Klein bottle. And you can see here how the patches are very nicely parameterized by the Klein bottle. You can see that this and this are the same. Okay, anyway, so this is a very interesting thing. We've actually used this in a number of different ways, but one includes texture recognition. So in textures, you can imagine that you can try to understand density of features of a particular kind, as functions on the Klein bottle, and the geometry of the Klein bottle then becomes important because you can actually do Fourier analysis on it. So this is work with Jose Perea. Okay, now the second thing, yeah, please.
Wait, if you take like 4x4 or 5x5 patches, is there any story or just goes through?
You get the same answers, but you have to choose different thresholds. So when you get to 5x5 patches, there's more variation, so you have to tighten your threshold on density very much. Okay, now we want to also be able to explore the data. So yes, we can do these signatures, but then we're going to understand, well, what actually is going on? How can we actually understand the space? And so that's this thing that we call mapper. So I'm going to give you a very simple example here. Here's a data set, and you have a projection going on. Now here, this is a projection on an axis. In general, we don't want to project on one coordinate axis, but something more statistically meaningful, like a measure of centrality or a measure of density. But anyway, we do perform this projection, and now we divide up the real line into overlapping intervals, so that we now have these inverse images. So if you look here at this point, I've now got 4 different inverse images. Notice that they are overlapping. So the orange here is the same as the orange up there. And so what I now do is now I perform a clustering operation internal to each of those layers, each of those inverse images of intervals. And so I will now get 6 clusters, and I connect any 2 of them if they contain points in common. So what I've done now is I've taken that original data set and just using this kind of function going off here, like a little bit like a Morse function. And from that, I can then recover the topology of the set. So, it gets at that. Obviously, it's not completely precise, but maybe oftentimes, maybe most of the time, you don't need it to be perfectly precise. You need it to give you understanding of what's going on. The reason I want to bring this up is because I'm now going to show you some analyses that we did. So remember, the question was now about what are the weights look like? What do the weight patterns in convolutional neural networks look like? And so that's a set of 3x3 things also. It's like pixel patches. And so what we found here was that when we applied this mapper algorithm with suitable parameters to this set of 3x3 activations within the neural network, this is what came out. And you can see that this looks exactly like that primary circle that we had before. And now you can see another role for persistent homology now is to say, well, you can show me this mapper model, okay, but it doesn't have a lot of theoretical guarantees around it. It's an exploratory device for now. But on the other hand, if I have a signature for shape, then I can actually verify that yes, it looks like a circle, but also it acts like a circle in terms of dimension, in terms of the Betty numbers. Okay. So this was done this is like the archetype data set for convolutional neural networks. It's called MNIST. It consists of images of hand-drawn digits. And the goal of the optimizer optimizes for predicting what digit is it that in a particular image.
This is a 3x3 response map for the 0.
Yeah, this is 3x3 map, right? But did I get it?
Yeah, so this circle is actually images, or it's
No, these are patterns. So each channel or each one of those grids in the convolutional neural network has associated to it a 3x3 array of numbers, which is, that is the pattern that one computes.
So this is a multi-layer, so you
Multi-layer, yeah. But this is probably, I'm trying to remember here. I think this is, I'll show you a multi-layer one in a little bit here, but this is probably one layer in MNIST.
Oh,
Two other sets, one other one I should say, called CFAR, which is different objects, and it's an object classification thing. And you can see here, yeah, that subprimary circle is still there, but maybe there's a little something dense here in terms of trying to find a bullseye. So now here's a more serious one. So this is on a network called VGG16. It's a 16-layer, probably, I think actually, 16-layer neural net that was trained on ImageNet, which is a very large data set of images, and it's a big classification problem with hundreds of different classes. So it's trained, in a very serious way. And so the question that you could ask for this is you could say, well, even in this network, I also have these patterns, these 3x3 patterns that I get computed at each layer. And again, I'm thresholding by density, by the way, because they're not all going to lie on this circle. Only the densest ones. There's going to be a lot of noise in the system. And so what you can see here is these are the different layers. This is 12 layers. The other 4 layers are sort of the end part and the beginning part of the thing. So these are the ones that are doing the real work inside here. So you can see that layers 1 and 2 are primary circle. We just see edge detection.
that's primary bottom layers, right? So
Exactly. Yes, that's correct. That's correct. So now layer 3, that's also got the primary circle. But what you can see there is, it's found some secondary circle stuff there, namely line detectors. And then something interesting happens here. Don't quite get it. These things are colored in such a way that the red part is the densest part. So even now, the densest part consists of a circle, but there's stuff happening in between. Layer 5, you have the primary circle there, but then a crossing in the middle has some non-trivial density, and so forth. So in other words, this is a way that you can identify, begin to start to think about what are the responsibilities of the various layers. And this is sort of in correspondence with the human visual pathway, which has several different computers in it. The first one being the primary visual cortex, which is the one that detects these kind of Klein-Bottle line detectors and edge detectors. But the higher ones do more complicated things. And you can see that the same thing has happened here. This is like in 12 layers. And you can see that it's capturing more and more stuff as it goes. Now, so this is a very solid big data set. Now, what we could do is we could also start maybe we're curious about what I could do with a lot less layers. and also understand what happens when I have very few layers. And so in this case, I've trained it for 100, epochs, 200 epochs, 400 epochs, and so on. And so what you can see is initially it's all kind of random. And by the way, these are rectangles here. Again, they're colored by density. So the red is the dense part. So what you can see happening is the first one, after 100, is pretty random. After the second one, well, it's starting to find that circle again. You can see that, like, this is red here, so and then the blue is low density. And nothing has happened in the second layer. It's not using the second layer at all. But now here's the third layer, and here you can see the primary circle is really quite distinct. So this is that same finding that we had before. Still nothing at the second layer. It's just kind of sitting there. But now something strange happens. This primary circle starts to disintegrate. So you can see it's breaking now. It's filling in again here. It's finding more and more things at the north and south poles, but less in between. And maybe there's starting to be some organization here when I get up to this point in the training. All of a sudden, I'm starting to see a little bit of a primary circle here, while this one is degenerating even more. So here I've got something in the middle, but now all I'm seeing are these 4 points. And so that is kind of the pattern here. And as you'll notice, by the time I get to 2000, this second layer has taken over the responsibility for this edge detection. We don't know why that's going on. We know that this network is maybe too small to do things, but the point is just that this kind of approach can give you a way to understand the learning process and what's.
If you have multiple layers, and do you expect that the learning would, because the lower level basically responsible for this edge detectors, and high layer, which is more task specific, right? So if you train this like longer, you do expect that the learning would moving from the lower layer to high layer?
We expect that if you have more layers, then we definitely expect, as we saw in VGG 16, that the responsibility for the edge detection, that's all the first layers are interested in. Right?
But that's after convergence, or how many epochs? This
Well, that on previous one, that was after, that's completely
Yeah.
converged. Yeah, that's right.
Have you done this kind of analysis on like a BGG size network where learning dynamics are saved?
Other studies?
Like something like this, but on like a VGG size network, the learning dynamics.
I see. Yes, no, we haven't. And the reason is we didn't want to have to retrain.
But I think there are some models where the learning is like publicly available, right? Like they save the weights, the whole process.
Yeah, this is joint work with my student Rickard Gabrielson, by the way, I should mention that, but no, the answer, we haven't done that. I agree, it would be very interesting. Okay, so the question is, can one use this information, this kind of thinking, can one use it now to actually improve performance of CNNs? So now I want to come to that signal processing stuff. So we've seen that what it's doing is learning edges and maybe lines. Suppose that we pre-compute those. Suppose that we compute those, recognizing that they're all organized in a Klein bottle. Okay? So what I could do is I could take a grid. So for the Klein bottle, I can build a grid from that square that you've got, and for each point create a function on the image. So that function takes a given pixel and it computes a dot product of that patch with the actual patch that's there. And so when you do that, this means now that we augment the input data with n additional features, where n is this grid. You're also free to modify the architecture, and we did some experimentation with that and plan to do more. But we found that the big gain was just simply in giving it that. So hang on. Yeah, so one can improve the learning rate. Now that's really not very surprising. If that would have been all that we do, then I would say you must, because of course you've already given it now the stuff that it needs to get to. So you would expect to improve the learning rate, and indeed you do. But I could also ask, what about robustness to noise? So in other words, suppose I take MNIST and I noise it up with a Gaussian kernel. Can I, then train the network on the clean and evaluate on the noisy, or vice versa? And so the answer here, what you see, what's happening is that, so the blue is a standard neural network, okay? That's the standard one. And then these others are various variants of ways that we've added features to this. And so what you see is that the robustness to noise, we get up to where it's like 0.8 in both cases here with our constructions, whereas the blue one sits down here at the bottom. It has a very hard time with noise, particularly at the higher levels of the variance. So doing this improves robustness to noise. And it also allows you to do generalization. One of the big questions here is about, are we getting to AGI, so generalized artificial intelligence? And I would argue that one big proxy for that is the ability to generalize from one data set to another, okay? And so this is an example again, where you can see we've got data sets. CFAR, I mentioned, Kaggle is another one. So the generalization there, and here is much harder, it gets at like 0.6% accuracy. But once again, the normal thing is down here, and the Klein model modified gadgets are up there. And just to give you another one, so this is two data sets of pictures of numbers, hand-drawn digits. One is house numbers here, and you can see this is a lot messier and more complex than this one. And so you can ask, though, can I take one and generalize it to the other? So in other words, train a model on one and then do it on the other. So we did both training on MNIST and evaluating on SVHN and vice versa.
One is the grayscale, one is color image. Do you need to modify the architecture of the model?
Yeah, this is a picture that you get off the web, like sort of remove the colors.
Oh.
Yeah. But indeed, the SVHN is a much harder data set. I would view it as that. Just it's not nearly as nice. But anyway, you can see here that once again we can get SVHN to MNIST generalization. So that's the house numbers, train on house numbers, and evaluate on MNIST, and we get. Up here, this is us, and then this is the standard models, and they look similar here, but notice that this is 0.2 and this is 0.4. So the MNIST to SVHN generalization is much harder to do, but nevertheless, one can improve it by adding these. How do we exploit this? Okay, so. What could we imagine doing now? So suppose that I instead want to do video classification, which is a much harder problem. The data is bigger, but it's also much more complex. And so the question is, what can I do? What can I do to do this analogous thing that we just did for static images for video? And I would argue that reasoning suggests that the object corresponding to K should be the tangent bundle to K, because the tangent bundle says that's trajectories in an image. And so you can see movements happening that way. And by the way, when I gave a lecture on this a while back, someone came up and said at the back, well, this is just a leap of faith. What the hell is this? And I said, yes, you're right. It's a leap of faith. That's what it allows you to do. Thinking about it and understanding it as a Klein model allows you to reason about it and say, indeed, that the likely thing that should work here is the tangent to the Klein model. And so we tried to, so now we didn't now have to go and do statistics on image patches or video patches. We said, but we're just going to try it and hope for the best. So we did it as an educated guess. Applied ultimately to a set of human motions from University of Central Florida. And the outcome, what is typically applied to this is something called ResNet, which got about, 5.5 accuracy, 5.5. And we immediately managed to bump that up to 0.7. We haven't really followed through with this very ambitiously yet. for reasons that I'll come to here in a minute. But nevertheless, this is an indication that this gives you a way of thinking about it. If you find a geometry, now it says, oh, now we humans can think of it and say, what does that mean in other situations that are analogous? And so allows us to do mathematical reasoning. Okay, now the problem with going further with this was that even in this situation, the tangent bundle to the Klein bottle, suitably modified, actually ended up being a 6-dimensional manifold. The tangent bundle is itself 4-dimensional, but we needed to add some stuff. I should say add some principled stuff. You couldn't grid all that. A 6-dimensional grid is hopeless. It's much too large. So we just took some little pieces of it. But suppose instead that I do the following. Instead of taking a grid on this manifold, instead I take its representation under an embedding inside Euclidean space and just use the coordinates of that embedding. So if I take the Klein bottle, it will embed in a 4D thing. And the tangent bundle to the Klein bottle here, we'll probably get away with 7 or 8 features instead of, this huge number of features that come from choosing a grid. So the question is, can we use these coordinates in conjunction with neural networks to produce moderate-sized networks? And the answer is, so this is work with Albin Liljefors, who has shown that one can do this. This is in the Klein bottle situation. We're working towards the video, but what we find is that, so love, this is the original one with the grid. And these two are 2 variants on this embedded manifold coordinates. And so what you find here is clean MNIST, everybody does the same. Robustness to noise, the manifold, one version of that is at 97.5 versus 96.2, which is not a bad improvement in there. But here it's very dramatic. This is for different values of the parameter of the noise. So this thing does very much better here. MNIST to SVHN generalization. Well, still, actually, this should be dark here. We're not quite there yet to improving over the grid thing, but we don't have to beat the grid thing. We only have to get close to it because we're building something is very much smaller. Obviously here here this is actually just for a circle, I should say. This is not the Klein bottle even, and so this is the primary circle, and so we really only have 2 additional features. So it's like 3 channels in your network as opposed to 64. So that's that, and then here we win with this other version of the manifold model. Okay, so we obtain better or comparable performance with much smaller neural networks and less computational cost. And it means that we can hope to extend the video, and we're working on it with 3D static imaging and even 3D video is all accessible if all you need are the coordinates of an embedding instead of a. Okay, so I have, okay. I now want to ask, is there a version of this? Is there anything like this that one could do for large language models instead? Can one do this kind of feature engineering for large language models? What kind of feature, how can I generate features? Okay, so anyway, large language models are performing miracles. We know there are problems with hallucination, lack of controllability. You need to adapt to specific vocabularies for specific tasks. I think I mentioned that before. If you really want to get much more fine-grained control, you want to add features without having to, get enormous amounts of data. So you would like to, guide the training process as much as possible so that you can get, specific, solutions for specific tasks. So there's not always enough data for the specific task. Okay, so images are pixel grids. The data set acted on by LLMs are something different. They have a geometry to them too, but it is sequences of tokens in an alphabet, right? So that's a different structure. So they can be words, or the tokens can be words or portions of words, also for punctuation and so forth. The sequences, they're not of a fixed length. And this requires building a new architecture, which fortunately the people at Google Brain did. This is in their 2017 landmark paper, which it says it's called Attention is All You Need. It's where they introduced so-called transformer models. And it emphasized the notion of attention, where you need to take a sequence, but you need to be able to be sensitive to connections between, you know, a token or a word at one point and a token in a different part of the sentence or a phrase. So, you know, it's sort of too complicated for me to go to sort of explain the transformer model, but it's been, you know, extremely successful. It allows you to do these tasks that we kind of marvel at, translation, and summarization, and so forth. It's interesting to note that the way these things work is you take your sequences and you estimate the probability of the next token, what that is. So it's estimating these probability distributions. We don't care about those distributions per se. That's not obviously what we're interested in. But the side effects turn out to be that you can feed these in, you know, feed in some description of what you want done, and it'll sort of find what it needs to do. So kind of an odd situation, but I think it's what we're in is the situation where what you're trying to optimize is not necessarily what you care about, but you care about the features that are being built inside the neural network to do that optimization. So anyway, here's the picture. So it's built as several, and these are encoder layers, as they're called. Oftentimes there's decoder layers on the outside. Okay. So anyway, the transformers produce embeddings. That is, it takes a sequence and it produces a vector in a high-dimensional Euclidean vector space. So, and the vector space geometry plays a role. You know, the distances in that geometry play a key role. And so this originated a long time ago that people worked with word embeddings. And now you understand that you need to do phrase and sentence and even more embeddings. So they produce an output sequence, but they also produce vectorizations on these sequences. So how can we use this method to introduce new features on sequence space? So here's something that we've tried. So one thing that you could do, if you have a sequence of words, you can say, well, each word has a part of speech. Sometimes a word can be two parts of speech. Let's, you know, you have to deal with that, but let's just assume that it's a many to one thing. So what I have now is, you see, I have my set of tokens T, which is my vocabulary, but I'm going to take something very much smaller as its image. So I have words, and I'm going to just assign to each word with a parts of speech tagger, it's part of speech. So now I have, say, maybe 1 million words in English, but I have maybe 10 parts of speech. Okay. So what I can do then is I can take any data set of sequences like this, of, you know, sentences, and produce the corresponding sequence of parts of speech. And so now I could do that. I could say, let me feed that to a transformer. Let me say I've got a sequence of parts of speech, and I want to predict the next part of speech. So. And so you can do that, and you try to predict the next part of speech. So the results of that experiment, well, let me say, so just to give you the sense of the encoding, right? This is the encoding we're talking about. Something like that looks like this. Okay. So anyway, this part of speech transformer is very small, right? I mean, this is a much smaller thing. You can do this, you know, get a good calculation of this pretty quickly without necessarily too much data. So the dimensions of the embeddings are also much smaller, like, you know, 10. So, so these can be appended to the embeddings in the large language model. So what I would do is I would feed the large language model with the original sequence and its embedding, plus this additional little set of features that come from the part of speech thing. So we hoped that this would produce an improvement. Okay, and indeed it did. We performed computations on a data set called Wikitext. Perplexity is a measure of confusion. It's related to entropy of the probability distribution for the next, next token. So, so perplexity, high perplexity is bad, low perplexity is good because it's a measure of confusion. So actually by doing this in a relatively small situation, we managed to achieve a 15% improvement in perplexity with just that. So we found that very interesting actually. And we said, well, so is there a point to say, maybe string analysis has a part that is syntactic coordinates that say what's the relationship of things as opposed to what the actual content of them is. And on the other hand, semantic, which is like really, what the individual words. And so, so one of the things that we did, we took the embeddings of these sequences of parts of speech and built a mapper model of them. And this is the sequences of a particular length, I should say. You have to do that in order to get something meaningful. But anyway, here's a model of sort of the sentences of a particular length. And, we look at them and roughly speaking, group A there has got narrative sequencing of a certain type. You can see implicit cohesion, where it says they contain seemingly contradictory ideas, such as expressing a particular perspective on divine events. Whereas group B has something that's more like explicit cohesion, where you say it became one of the top grossing productions of India that year and earned 1.86 billion. Now, looking at all this, of course, it's possible to hallucinate yourself in thinking that you characterize the group. I mean, if you've ever done connections, the game, the New York Times connections game, you'll know that you sometimes hallucinate because you look like you've got certain of these groups look like they're meaningful. But nevertheless, for what it's worth, take it for what it's worth here. This is what comes out, but it says that we've kind of got a model for the space of kind of sentence archetypes. Terms of syntactic coordinates. What we would like to do, what we want to do now is to sort of add that semantic component. So what we'd like to build a different low resolution alphabet or low resolution vocabulary, which instead of having parts of speech, instead has things that you might get out of a thesaurus. So dog, cat, elephant, those are all animals, and the high level construct is animals, and the lower level ones are those. Similarly here, tools and emotions. So one thing that you could do is you could now say, let's take a sequence of words, and let's generate its concept sequences. We haven't done this yet, but my feeling is that this is going to be, doubtless is going to produce some kind of improvement here, but it's also going to produce, I believe, things that are more interpretable, because it's operating on something coming from a thesaurus, which is what humans use. We're using that structure in a serious way. Yeah. So this would be high level semantic coordinates instead of syntactic, and it would require this information. We've actually done a couple of studies on the words. Actually, it's kind of interesting. The words in the thesaurus form a directed graph, because the dog is an animal, and so there's that relationship. So John Kleinberg at Cornell developed two functions on graphs, on the vertices of graphs. It's related to page rank, but instead they're called hubs and authorities weights. And so when you take that network and produce hubs and authorities weights, what you find is that somehow when you look at the graph of hub versus authority, in the upper left are words that are very kind of high level conceptual things. And at the lower right is very specific things. So I have a feeling that in addition to other things, is something that one would want to include in one's analysis of these words. And I see that I am out of time here. So I will just tell you what I was going to tell you about, which is autoencoders to be used to generate understandable features for the neural network. So one of the big directions now is called mechanistic interpretability, which means that you're trying to really understand what's going on inside the neural network. So in order to do that, one uses autoencoders to produce more interpretable features. There's a long way to go, and I have a feeling that the stuff I'm talking about the semantic coordinates there, should be an important input to that whole enterprise. Anyway, I'll stop there and thank you for your attention.
So, questions, comments?
There's anything interesting if you try to look at the persistent homology of the image of the token alphabet in the vector embedding space?
I think you might. I think there's a lot to be gained even by persistent H0, frankly. Persistent H0 is going to do you a lot of good there, I think, because that's what you're looking for in terms of you're looking for clusters and so on. And you know, this gets used in a very precise way. That's not even just of scientific interest, but if you're familiar with RAG, you know, I forget what it is, something augmented retrieval. Where you know you're trying to have a query and find the documents that are relevant. It's exactly that kind of question of clustering within one of these embedding spaces. So there's a good use case for that. Yeah.
For the clustering for the words, what were the projection or Morse type functions that you used for your mapper model to get the two groups?
Oh, for that, yeah, it was a centrality measure. Yeah.
So I guess why should we expect that a Klein model? Like we know that a Klein model has shown up, right? Like in this like edge detection thing. Is there a good reason why we should expect the Klein model to be there, or is this something that currently we just know is there and we don't really know why?
I think we kind of have an idea why, because you know the primary visual cortex has detectors both for edges and for lines.
Okay.
So if you want to try to build some kind of minimal geometric model that includes both edge detection and line detection, you're kind of forced to this. So I think there's a good reason for it, yeah.
Maybe it's because topologists love Klein models. They've grown up with Klein models.
You know, so many people have said that. You know, they say, well, you know, yes, you showed me this picture, but why can't I just lay them out on a torus and stuff? And I try to explain it to them. But I will say, when we did this, and we did the homology computation, I said it's going to be a torus. And I was wrong, and I was very happy to be wrong, because it's much more interesting.
Certainly, yeah.
I guess
Still,
yeah.
Other questions, comments?
So we just saw that adding the parts of speech model or this purely syntactic thing resulted in a kind of significant decrease in perplexity. And then kind of like dual to that, you presented the ongoing work on doing a purely semantic kind of thing. Which one do you actually think will do? Do you expect the semantic thing to have a bigger decrease in perplexity or a smaller?
I do, but I also expect it to have a bigger effect on interpretability. That is to say, I think that the features, the networks that you train with that as a thing in there, I think those are going to be much more closely tied to the way humans do things.
Yeah.
The thing is, building that, I mean, I sort of put it up there and it looks obvious. Well, sure, animals don't. But it's harder than you think. In other words, building that, you know, the right kind of word concept embedding is you got to find the right one.
Any more comments about this very interesting subject? And let's thank Gunnar again.
Yeah.